Okay, question 4 is about a pulsar, which is a type of star, and they give off short bursts or pulses of X-rays at regular intervals, which we can pick up on Earth. So some pulsars will emit radio waves, others will emit X-rays. Now, what is a property of waves that is the same for both radio waves and X-rays? Well, the one key thing they really want you to say is they have the same speed in a vacuum. Okay. Actually, in any other mediums, their speeds will be slightly different. Okay, but in a vacuum, they all travel at the same speed. I think they'll also accept it if you say that they're all transverse waves or they're all electromagnetic waves. They can all refract, they can all reflect. Okay, those are all acceptable answers, but I think this is probably the best one. State 2 properties of waves that are different for radio waves and X-rays. So although they travel at the same speed, one of the key things that is different about them is they have different wavelengths. Radio waves are very long waves, in the region of meters or even up to kilometers, while X-rays, a tiny fraction of a millimeter. And if the wavelength changes, then from our speed equals wavelength times frequency equation, then the frequency must also be different. And remember, the frequency of any wave is determined at the source. So when the waves are created, the frequency of the vibration is what causes the waves to have their frequency, and that shouldn't change no matter what happens to the waves afterwards. Whether they reflect, refract, diffract, the frequency will always remain the same. Now part B says the graph shows 5 pulses of the signal from a pulsar. So we can see how the signal strength changes over time. And you're asked to explain how the graph shows that the signal is not digital. Now if we have a look at the point on the graph, I'm going to choose this point here. So after about, what's that, 1.6 seconds, if I was to ask you what the signal strength is, the signal strength is about 0.2 in whatever units they're choosing to display this. Well, a little bit later, the signal strength is 0.4. A bit later it's 0.6, and again have a look, we can take a whole range of different values for signal strength on here. Okay, now a digital signal cannot do that. Okay, a digital signal is one in which, well, at least a binary digital signal is one in which you can have only one of 2 states, okay, discrete states rather than a continuous change between them. So the signal strength can take a variety of different states, not just on and off. Okay, so it's got a continuous range of values. Now when you look at the graph above, you can see that the state changes from 0 to 1 gradually. You get this gradual sloping up. If you were looking at a digital signal, then it should be in a very short amount of time go straight from 0 up to 1. The next question says use the graph to estimate the average time between each pulse. And the most accurate way of doing this is, like I've shown on the diagram here, to look at the time taken between a number of pulses. If you just did it for one pulse, then you can have bigger errors, or a bigger percentage error for every measurement you take from the graph. So I've done it for all of these pulses here. So this is now the time taken for 4 pulses, where I've got 5.7 seconds when the last pulse comes in and 0.3 seconds when the first one comes in. So the time between all 4 pulses is 5.7 minus 0.3, so 5.4 seconds. I want the time for each pulse though, so I'm going to divide that by 4 and I get 1.4. And the final question says calculate the frequency of the pulses in the signal. Well, we need to use another equation here, and the one we're going to use is frequency is equal to 1 over period. We've just worked out the period of the pulses from the last part, and that's 0.71. And remember that frequency means the number of cycles or waves per second. So this is saying that every second we get 0.71 cycles, so less than 1 cycle per second. We also need to give the unit, and the unit for frequency is hertz, which should be a capital H, little z.